So, my talk, Unikernels, who, what, where, when, why, and I got that in the right order. So, imagine that you have to build some sort of application. So one of the first things you're going to do when you need to build that application is select some platform to build it on. I don't know what that platform might be. Might be Windows, might be a JVM, could be any number of things. Now, since this is the Zen User Summit, you can guess that I'm going to want that platform to run on top of Zen in some case, because I'm going to want it on my private cloud or some public cloud or something like that. So the question I want to answer is, what is that platform going to look like? So if this were 10 years ago, you'd have two choices. You could choose Linux or you could choose Minios. Linux, full-featured operating system, does everything you want and a whole bunch of things you probably don't want. Minios does pretty much absolutely nothing. Gives you a few C library routines that you have to build everything in the world on top of. So very, very split 10 years ago. A couple years after that, the Zen community got inspired and ported a whole bunch of other full-featured operating systems on top of Zen. So now you could choose FreeBSD or Windows. A couple years after that, sometime in 2007, I believe, there were two of these unikernel things that popped out into the ether. HalVM, which is the one I wrote, and Mirage, which is, has been mentioned several times today, and is a different unikernel. Shortly after that, people started going, oh, embedded Linux, that actually makes sense on top of Zen, because now we can shrink the stuff that we're putting on top of Zen. Maybe we should use that. And then a few weeks ago, my company announced that we have a port of FreeRTOS to Zen, so now you can build your real-time operating systems and run on top of Zen. So the question I want to answer in this talk is basically, which of these are you going to use, when are you going to use them, and why are you going to make that choice? Now, in particular, I want to focus on one part of the spectrum that goes from gives you nothing to gives you everything in the world. And it's sort of this purple part over slightly to the, let's see, that's the right side of the screen, which is this Mirage, HalVM, OSV unikernel space. So a unikernel, I will define it right now, also known as library operating systems. I believe in the 90s, the research community might have called them exokernels. Bunch of other names if you prefer those names. But basically, these are single-purpose, usually single-language virtual machines that are hosted on a minimal environment. So in this case, they're hosted directly on top of Zen with no intervening operating system, much as Don described in the OSV talk previously. So my talk, I'm going to separate it into three sections. I'm first going to talk about some of the advantages and disadvantages of unikernels. I'll skip over some of it because you just heard Don talk about some of the advantages of unikernels, so I don't want to bore you too much. Then I'm going to move into some places where the company that I work for, which is called Galois, has used them in the past and where we've been successful, and actually one case where we were not very successful, and I'll tell you about why that happened and what the lesson you can learn from that. And then finally, I'll conclude with sort of general rules that we think apply. So to start off, I want to do sort of a very quick briefer on unikernels. You've already heard one, again, from Don, but I'm going to come at it from a very slightly different angle. So if you think of a traditional system, you start at sort of the ground level with an operating system kernel, your Linux kernel, your NT kernel in Windows, whatever it is you want. Built on top of that are usually a whole mess of libraries that do a whole bunch of very interesting things like render graphics or do compression or crypto or whatever it is you want to use. And on top of all of these libraries are built a set of applications which are running concurrently. So going back to my original case where there was an application I want to build, so there's my little application there. Now, I was just instructed to build that one application, so this picture is already a little misleading because I don't need those other two applications, so we'll cross them out. So the interesting insight that unikernels have is if you look at this application and you see all these libraries and all these and the operating system kernel at the bottom, is that you don't actually need all of that. What you need are little slices of each of these libraries, and what you need is a little slice of the operating system kernel. You don't need all of it because you're not going to use all of those libraries in every application. It just doesn't really work like that. So the unikernel insight is, hey, can we build systems such that we take our applications and then we figure out the parts of these libraries we need, and then we cut out all the parts we don't need, and then just sort of glom it all together into a single binary that's going to run on top of Zen or KVM in the case of OSV or what have you. So why would you do such a thing? From our perspective, I think we've learned that there's three main reasons you might want to do it. You might want to do it to save money, you might want to do it to save time, and you might want to do it to improve your security story of your system. So first of all, why does this save you money? It saves you money because we're reducing your memory footprint. We're greatly reducing your need for a disk. And you have a reduced computational burden. I'm not going to go into that too much because Don, again, did a great job in the previous talk describing why unikernels can save you some computation. But what this adds up to in the end is that you can use less powerful virtual machine classes for the same amount of work and save money that way, which means that either you use a less powerful virtual machine from Google, or if you have your own private cloud, you can put more things on your single bit of hardware. It was interesting, Conrad mentioned this morning in his talk that you could get some of these unikernel things down to as low as 32 megs, and that was very impressive, I guess. We actually have seen unikernels as small as 4 megs, and they would be smaller, but Zen gets upset when you have a virtual machine that's less than 4 megs, or at least it did a version or so back. So you can get these things really tiny and save yourself a good bit of money. So the next reason is performance. Again, Don did a great job, so I'm not going to spend too much on this slide, but because you're using a unikernel and you're stripping out a lot of sort of excess stuff in your system, you get a reduced memory footprint, you don't have extraneous processes taking up your CPU, and you have fewer schedulers in your system taking up latency. So you get faster load times in general, and I'll describe that a little bit more in the future, and you get lower latencies in terms of network and other performance. Moving right along, sort of the final reason that at least we look at unikernels is security. So one of the benefits of unikernels, again, is this reduced code size, which means that you have a reduced attack surface for someone trying to find flaws in your program. For those of you who have been looking at sort of return-oriented programming and similar attacks, it also means that there's less gadgets sitting around in the heap for people to use to attack you. The other thing is that unikernel libraries are always customized to the application that you're running, which it means that different unikernels that do different tasks look different and don't have the same code base underneath. So an attack that works on one may not work on another if it's not using that exact same library, which gives you some nice properties so that, for example, the unikernel I'm working on is called the HAL VM. It's unlikely that you will find an attack that will work across all HAL VMs everywhere, unlike an attack against, for example, the Linux kernel, which is going to break all your Linux installations everywhere. The final reason we like unikernels is because by keeping things small and keeping everything single purpose, you can use things like the XSM policies that we talked about earlier, or other versions of security to build very strong walls between the components you build in your system, limiting each component to exactly the privileges it needs to run. And so you can get some very nice security properties out of that. I'll talk about one of those later, I believe. So in general, improved security through less exposure to sort of generalized attacks. You can greatly reduce privileges in many cases, and you get this reduced attack surfaces. So with all those three wonderful things, I'm sure I've sold you all on using unikernels for everything all the time. So let me be honest here and tell you a few reasons why you might not want to use a unikernel. So reason number one is sometimes you really want a lamp stack that involves a whole bunch of operating systems running with a whole bunch of libraries running on top of an operating system kernel. If this is what you want, it ain't broke, so don't fix it. And just use a Linux kernel and everyone will be happy. Works just fine. The second reason, which is a bit more subtle, is that, as you may recall, one of the advantages of unikernels is that you could take these narrow slices of libraries that exist and combine them into a very custom thing that's going to run on top of your Zen system. There's two kind of issues for this. First of all, many unikernels use sort of, for example, the HAL VM runs the Haskell programming language. The Mirage operating system runs OCaml, which is a programming language. It could be that all of these bits of libraries that you want or need don't exist in those programming languages, which means that you are going to have to write these little bits. Even in the case of something like OSV or Minios, where the language of choice for unikernel is C, there's a lot of unintended consequences when it comes to C libraries. My favorite example of this is that there's a POSIX function, local time. And what local time does is take the number of seconds since the epoch and give you a date that gives you month, day, year, whatever. One would expect that one could just link this into your program with no problems. It seems like that should be no problem at all. Turns out, local time uses your file system. So it needs fopen, it needs a POSIX-like file system format, and so on. Because what it does is first open up a file to see what time zone you're in, and then it opens up files based on those time zones to get information about how it should compute those dates. This happens all the time in C libraries, where you think you're using something which is just going to take something in memory and do some computation and put something in memory, but actually it uses this library, which uses this library, which uses that library, which uses a file system and the network and what have you. So in those cases, there is some time required to go and whittle these down and replace these sort of key junction points. So in the end, there is a lot of software for Linux. With a unikernel, you will end up either writing these bits and pieces or rewriting bits and pieces to limit the amount of sort of exposure you have to the vast Linux library conglomeration. And the final reason why not, I mentioned that unikernels can save you money. I really should have put an asterisk right after that. The savings you get from unikernels come from avoiding some expenses. For example, they quite easily remove the need for disks. They can quite easily lower your memory footprint, and they can also quite easily reduce your computational burden. All these things that can let you use a lower powered VM and save some money. Of course, if your application is, for example, a scientific computing application that needs gigs and gigs of memory and is going to peg the CPU no matter what you do, you aren't going to win in this case. And so in that case, unikernels may not be the best decision. So with that sort of background information, what I'd like to do now is shift away from sort of generalities and talk a little bit about cases where the company that I work for has actually used unikernels in the projects we've done for some of our clients. And I'm mostly going to say that we are successful in do that, but there is one case that I'm going to tell you about where we were not, and I'll tell you what we learned from that, and then I'll conclude with general rules. So a little bit about the company I work for first. It's called Galois. It's not Galois, Galois, it's French. The mission of the company is to create trustworthiness in critical systems. What we do is R&D work in computer science. What this means for you and this audience, and the whole reason I have this slide, is that what we do is we find customers with problems, we build them prototypes that solve their problems, and then we move on to the next problem. And so we've had lots and lots of cases where we take a look at a customer problem and go, does a unikernel solve this or not? Is it an interesting technology here or not? If so, we use them and then we learn something from it, or we don't. And so we've actually used unikernels on 6 or 7 or 8 projects over the last 5 years. And so that's what's basing some of this work that I'm telling you about. So the first question is, should we even think about using a unikernel at all? And we've discovered, at least in our work, that unikernels are useful in sort of 3 main use cases. So use case number 1, you can think of is on your machine. So these are usually embedded, single host, deprivileged security apparatus that are running on a single machine. Second use case you can think of as on your network. And in this case, we can use unikernels as sort of lightweight, highly scalable local network capabilities. Again, because we do a lot of security work, there's a bit of a security flair in this as well. And the final use case is sort of highly flexible, highly mobile, on-demand network nodes in the cloud. So that's sort of outside your network. So I'm going to go through each of these use cases. So the first one, we've had a couple slides today on what does Zen look like when it's running on your host. So here's yet another one. So you have your box and Zen's running at the bottom, and you have DOM0 and a DOM-U. That DOM-U is using, for example, a network card, a virtual network card. The way that works is it sends messages back to DOM0, which does some finagling, and then sends them out your network card and onto the wire. So it occurred to us, and it occurred to a bunch of other people, if you look at this picture, that wouldn't it be neat if you could take this picture and you could break that arrow, and then you could put a box where that arrow used to be, and then you could put a different arrow from DOM-U that goes to that box that just looks exactly like the virtual network card that it used to use, but now instead of going to DOM0, it goes to our little box before it goes to DOM0, which is a really interesting way to build a whole bunch of interesting security apparatus. It gives you unavoidable encryption if you want. It gives you unavoidable filtering or tunneling. Basically, what it allows you to do is put any sort of filtering or tunneling box outside of the operating system you're protecting. So in this case, if Windows has a bug or a virus or whatever, even up into a sort of kernel level virus, it can't avoid going through your VPN tunnel, or it can't avoid going through your filtering mechanism. This is really useful from a variety of security purposes. And when we actually built this, we built some actually much more complicated infrastructure around this, which again used XSM to make sure that information flowed in exactly the way we wanted to. And we were mostly very successful in doing this work. Mostly, of course, is a danger word. Whenever anyone says mostly, you should look at them quizzically and wonder what they're hiding from you. So I will tell you what I'm hiding from you. One of the things that our client was interested in was, hey, instead of sending all the network packet information to DOM0, which also has your disk and a bunch of other things, could you maybe make a unikernel that was the device driver for your network card? And then it would go off to the device driver, which would be separated. Again, XSM policy, it's going to be great. And this turns out to be one of the places where unikernels don't really help you all that much. And the reason is this. Unikernels, as I said, you end up building or rewriting a bunch of these little library snippets to make up the unikernel you want to do. Device drivers don't have a lot of snippets in common between them. You write a network card for this PCM-CIA device, and then if your client, for example, midway through your thing comes back and says, hey, can you actually switch it to this USB-based device? Now you have to throw out a bunch of code you wrote before and write a whole bunch of new code for your USB thing, which turns out is exactly what happened to us on this particular project. So one thing to keep in mind with unikernels is that because they are specialized, they become brittle in some cases. And so one thing to think about when you're thinking, should I use a unikernel for this project or not, is where your client might change their mind on the details and how much those details are going to impact the unikernel you're building for them. So in this case, we should have seen very easily that our client could change their mind about exactly what device they wanted to support, and then gone, oh, if that happens, we have to change a whole mess of code underneath, and maybe chosen something else. And in the end, we implemented it with the Linux kernel. But something to keep in mind when you're dealing with unikernels. Between the Zen Developer Summit and now, I still haven't thought of a good transition slide for this point, so here's some bunnies that are very cute. So clear your mind. And on to use case number 2, which is unikernels protecting your network. So one thing that's been, I think someone mentioned this earlier today, but one of the things we're learning in network security is that firewalls are nice, and please don't hear anything I'm saying as you should tear down your firewalls and do something else. But firewalls are going to be broken. Either someone's going to break through them or they're going to get around them somehow. And this is just a fact that we all need to learn to live with. So one of the new questions in security, particularly around IDS and SEIMs and all these sort of things, is how quickly can you detect that someone has broken into your network, and how fast can you respond to that attack? So one thing we've been using unikernels in this space for is using unikernels, which again can be implemented as very tiny little nodes on a Zen box, to add a whole bunch of false infrastructure or confusing infrastructure to your network. And what this does is when the attacker gets on your network, eventually, because they're going to get around your firewall, and starts doing scans to look around your network to see what's going on, there's a whole bunch of confusing stuff on there. Hopefully this slows them down, hopefully this makes them make mistakes, and hopefully, ideally, this makes it easier for you to catch them. Unikernels make a great base for this. Again, as I said, they're very small, so you can host hundreds, if not thousands of them on a 1U rack box. But additionally, they boot really fast, and they can do a whole variety of different things. So you can detect a certain sort of attack and respond to it in different ways very, very quickly in a much shorter time span than a human going, oh, I need to run this program now, can do this. And so we've had a couple of projects in this area where we use unikernels to sort of do automated defensive response if an attacker is on your network. So the final use case I want to talk about today is sort of leaving your network and moving on to the cloud. So there's a bunch of different solutions for hosting applications in the cloud, and I'm not going to go through all of them. You all know them all. There's Docker, there's OSV, there's a bunch of other things. You can just set up a Linux virtual machine in Amazon and trigger them pretty easily. Unikernels have two major advantages over most of these systems. The first being they're very nimble because they're very small, and they scale massively, also because they're very small. This is true as long as your system fits in a certain mold. And I have a sort of general rule of thumb that I use for determining whether you're in this mold or not. And that is basically, do you need a local disk? If you think to yourself about the service that you want to put in the cloud and you think, I need a disk to do this, my experience is that as a rule of thumb, unikernels are probably not what you want. On the other hand, if you think, oh yeah, clearly this doesn't need a disk for anything, then unikernels might be something you want to think about. So let me give you an example of one of the things we were thinking about doing in unikernels. So I travel a lot to conferences like this, and I go to hotels and coffee shops and whatever, and they have free wireless, passwordless wireless, which is supposed to make me very happy because I get free internet. But the truth is, as I do security, this makes me very unhappy. And the reason this makes me very unhappy is because I know about this tool called Wireshark, and I know how chatty my laptop is and how easy it is to look and figure out what I'm doing on the internet. This makes me very unhappy. Eventually, I became a little more happy with this because I discovered this tool called SSH. And SSH allowed me to log back into my machine at home and then tunnel all my traffic through an encrypted channel back home, which then bounced out to the internet, which made me a little more comfortable about using internet cafes. So that's nice. The trouble was, and this worked a few times when I was traveling, last year, for the last year's Zen Developer Summit, I was in Scotland. Where I normally live is in Portland, Oregon, on the west coast of the US. As you might imagine, SSH tunneling all of my traffic from Scotland to Portland and then usually back to Scotland really was not fun. Really increased my latency quite a lot. So I thought to myself, wouldn't it be nice if I could take whatever machine I had in Portland and just zip it right over to England or Scotland or somewhere in Europe at the very least, and then I could connect to it then. And then I thought to myself, hey, wouldn't it be nice if I actually just had a whole mess of these sitting around Europe, so if I ever needed to connect to them, they were there and I could do them. Or maybe I could throw some on the East Coast too, that'd be great. And in fact, while I'm at it, I'll just throw them everywhere in the world, including Antarctica, because why not? Of course, now that I've got things sitting all over the world, I don't necessarily trust all the governments and entities in these cloud server farms that I might be using. So it might be nice if I could bounce the traffic from one of these nodes to another in some sort of encrypted way so that my traffic couldn't be learned from everyone, which of course leads to Tor really, really quickly. So unikernels are great for things like Tor. Why? Because in Tor, you want a whole mess of nodes everywhere, all through the cloud, to bounce your traffic everywhere. Unikernels make a great host for that because, again, they're small, they're very nimble, they're network responsive, as Don was talking about, and so you can add a whole bunch of nodes to your Tor network very quickly, very easily, and in response to the need that you see. The other thing I wanted to talk about in terms of cloud is that unikernels are shockingly nimble, which makes for very bad demos in some cases, but the Erlang guys figured out a way to make them very cool. So as Don mentioned, there's a unikernel called Erlang on Zen. I think they changed their name, but that was the original name. And they had this very interesting demo where they had a web front end, so you did an HTTP request. The front end noted that you had that request, booted up a unikernel in real time behind that to satisfy that request, which were then responded, and then shut down. And you couldn't tell this was happening, at least according to human timescales. I didn't do any sort of high-grade millisecond level performance testing, but it was kind of an interesting, wacky demo. It was a very cool demo. It's a little over the top. I can't really imagine many web services where it makes a whole lot of sense to boot a full unikernel, do something, and then shut it down every time you get a web request. But think about what that means. So what that means is that you have a level of dynamic scalability which is incredible. In subhuman comprehension, even timescales, you can quickly boot up hundreds of unikernels to respond to a flood of traffic in your system. And then, once that flood of traffic is gone, just kill them all. And then, when the flood comes back, you're ready for it. Because again, you can boot these things in milliseconds. So this is what I mean by flexible and responsive. Unikernels give you a case where you can, even more than many other cloud capabilities, scale your service in reflection of user demand. So that's about all I'm going to say. There's some general rules that I think you've probably learned by now. Unikernels, what are they? They're a lightweight mechanism for implementing single service components. That's a very important bit. These are usually single service. They do one thing, they do it well, and they do it cheaply. Who might want to use them? Designers of cloud services, people doing local network security apparatus. This is a great way to do it without exposing yourself to even more attacks by building more security apparatus. Or for people building low-level security services on a server or a laptop or other such devices. Where would you use them? They're useful for securing or rapidly deploying these lightweight or security-sensitive services. And I've described a whole different number of situations where you might want to use them. And why would you want to do it? To save money, to improve your efficiency, or to improve your security. So, in summary, unikernels, useful. But there is this equation that you need to think about. Is the cost savings, the time savings, and the security benefits of a unikernel going to outweigh the fact that you're probably going to have to do a little more engineering work than you would have in a more standard system, and the fact that what you're going to build is perhaps a bit more brittle to user change? I can't make that determination for you, but I'd be interested in hearing what you were thinking about that. So the question is, where will you use them? I put links to the two unikernels I used the most, which are the HalVM, which is the one I wrote, as well as Mirage, which is a Zen subproject out of Cambridge, very cool. I would also recommend OSVs, doing some cool things, so you should go talk to Don as well. And in general, if you use a unikernel, those of us in the community would love to hear why. Or if you thought, in fact, I might use a unikernel, but actually in the end we decided not to, that would also be really interesting stuff for me and others to learn. So that's all I have. Thanks for your time. Yes?
Question on the local disk. Does that apply to local disk or something like a NoSQL data store that's horizontal scale and the contents of that individual local disk don't necessarily be backed up?
So the question was, I mentioned earlier that a rule of thumb is, does this service need a local disk? And if it does need a local disk, that might be an idea, suggesting not to use a unikernel. And so the question was, is that true even for certain kinds of disks where perhaps you have a disk, but the contents of that disk are not persistent? Is that another way to ask your question? So that
From other data stores.
okay, so where they can be reconstructed from other data sources. So certainly that's a case where you've basically saved something from being almost definitely not a unikernel to maybe you could make something work. The reason I tend to avoid disks in the unikernel work that we do is because you have to pay for disks on certain clouds. And so I like avoiding that fact that I'm paying for something. And so typically in some situations where we might want a disk for auditing or for logging, we do that over some sort of network service and then just avoid the disk entirely. I could imagine that if the disk contents, for lack of a better word, were something you could regenerate and keep in memory, that would also be a case where that might work with a unikernel. Again, these are rules of thumb, so there are probably cases that I'm not thinking of or where a disk works just fine. That's just been our experience using unikernels.
So what do you usually use when you What do you usually use when you need a persistent storage, and maybe you use NFS or something like that? And please don't say SMB.
No, no, not SMB. And in fact, not NFS. So there have been some cases where we have done unikernels that did need a disk, and it's perfectly, you can do it. It's a matter of finding a file system that will work for you on that disk. You know, we wrote a file system in Haskell just for this purpose, so that we could do this on a disk. In other cases, we find other ways to use a disk. So you can imagine going through a REST API or something like that as a way to access a sort of notional disk. Again, in many of the cases, what we don't really need is a full disk or a full file system. What we need is either a configuration file, in which case we just sort of pass along a tar ball and then expand it in memory and just use it that way. Or even more common, what we need is sort of logging or audit capability, in which case we use some other form of networking to do that. And so we basically pull out the disk parts and put in a network-based solution.
You mentioned spinning up like hundreds, for example, of these unikernels. That would be on a single machine. And what would be the reasons for doing that instead of having one unikernel handle those hundreds of requests, for example?
I'm hesitating because I want to make sure I want to say what I'm about to say. Yes, I think I do. So yes, typically this is hundreds on the same piece of hardware. And there's a couple reasons to build hundreds of virtual machines rather than one virtual machine that handles them all. The first is to put walls between them, right? So if I have 100 VMs, if an attacker breaks one of them, they have to go through Xen to get to the others, right? So that's one reason. And another reason, which you can get around in other ways just using a single one, is, for example, in many cases we want them to have separate MAC addresses, and a much easier way to do that, besides building a whole bunch of tap devices by hand and all that sort of thing, is to just build separate virtual machines. And then they not only have different MAC addresses, they act much different, which can be very useful. So that's two reasons. And I should say, we've booted, I think, hundreds in some cases, although more commonly in our experience we've booted 20 or 30. There was a really interesting talk at this past Xen Developer Summit from some folks who were trying to boot thousands of virtual machines on a single host, and some of the interesting scaling problems they had with Xen. And so if you're interested in that subject, I would encourage you to go look up that talk. It was a really good one. I can't remember what company they were from. Do you remember, Russell? Yeah, I was thinking NEC too. So we're both going to guess NEC, and hopefully we haven't insulted anyone too badly. But yeah. Any other questions, comments, concerns, insults?
I just wanted to add as a comment too, not only was there research being done there, but I think if you look back at the recordings of Developer Summit from a year ago, some of the Xen platform team people were actually working to try to enable scaling to the thousands as well. So I mean, there's been analysis going on. It's not there yet, but I think one of the things that's actually really, really cool is that throughout the ecosystem, there's a realization that things like this are going to change the way we do everything. So there's work being done within the hypervisor layer to try to enable that day when you're going to roll out 2,000 VMs on your box because it seemed like the right thing to do, and it'll just run. So I mean, we've got that vision there, and it's not all together yet, but it's working in that direction. I think it's a question more of when rather than if.
Yeah, I should say it seems like there's a whole bunch of people working on sort of the scaling problem of booting a bunch of unikernels on Xen. I should say booting a unikernel on Xen makes an incredibly bad demo. So when I first made the HelVMs and booted them, I did sudo xm at the time, create. this LVM, and it just looked like I was starting a Unix process, which then exited. Great, that's exciting. It's when you want to build hundreds of them quickly that the current Zen tools start getting a little sluggish. And so that's what a bunch of people are working on. But they actually, if you're just building one or two at a time, they boot really, really quickly. As I said, the Erlang guys got it down to web response speeds. So that's sort of the state of the art right now.
Have you done any performance work looking at the difference between starting these up and shutting them down and what containers take?
So the question is, have we done any performance work? So I know if you're really interested in performance, I would certainly ask the OSV guys, because I know that they've looked at performance quite a lot. I've done some performance, and I can give you some sort of experiential results. So for example, I frequently in some of my test cases boot up unikernels too fast for the Zen tools to handle. So they will boot up, do something, and then come down so fast that the Zen tools are still waiting for other parts of the system to catch up, and then you get this interesting long Python or C error message about everything going to hell, when actually everything worked fine. So they boot up really, really fast. Network speeds, I haven't done any benchmarks on mine. I know the OSV guys have done some benchmarks. I know the Mirage people have done some benchmarks. You can do some very, very fast network handling with unikernels because there isn't a sort of full-featured POSIX OS in the background trying to keep processes separate and all that sort of thing. So many of these systems use no copy or networking all the way from card to unikernel, basically. So you can get some really significant performance benefits in that case. Again, I haven't done any what I would consider rigorous benchmarking myself. I would refer to you to Anil at the Mirage project, or Don or someone else at OSV about the sort of, I know they've both done some more rigorous benchmarking than I have.
Okay, thanks.
Anyone else?
What's Tor?
Tor is the onion router. That's what it stands for, I believe. And basically, it's a anonymization network for TCP traffic. So you basically hook your system up to Tor, and you send packets in, and they get routed and bounced all over the world through various encryption channels and interesting shenanigans. They pop out somewhere else, and no one can tell that you are the source of that request, and no one can tell that the response comes coming back to you. So one of the interesting things about Tor is that it is greatly enhanced the more nodes there are in the Tor network, because it adds basically more noise to the system and makes it harder for an adversary to control enough of the system to detect that it's you and not me sending this traffic. And so unikernels in this case allow you to build a lot more nodes using sort of the same hardware underneath, which is pretty cool.
I believe you mentioned embedded systems. I hope I'm not confusing with Don.
Yep.
So have you ported HalVM to like ARM processors?
So I'm going to separate two unikernels here. Yay. So the HalVM, no, it's on my to-do list, but I haven't done it yet. Other work at Galois, so that is not the HalVM, is we ported FreeRTOS to Zen, so you can run a real-time operating system as a Zen guest. And so in this case, what we're doing in that space is we were interested in building security and reliability components for UAVs in this case, or drones of some sort. So in this case, you run your core drone autopilot as a FreeRTOS guest on top of Zen, and then you can run your webcam or whatever else you're running on that as a separate guest. And then even if someone screws up the webcam software, it's not going to impact the autopilot, which won't send it crashing into things, which is something we like to avoid in the drone space. So in that case, yeah, we're using unikernels for embedded systems, and they work really well, especially because, again, small is very good for embedded, so works quite nicely.
To that point, are unikernels then running on an embedded system on a hypervisor? So they're still on a hypervisor, even though they're on that embedded system.
Yeah, so in one of our experiments, basically we have a quadcopter that's running, it's on an ARM chip, and I don't remember exactly which one, so forgive me, that's running Zen. One of the guests of that system is the FreeRTOS that's doing the autopilot, and we have a DOM0 and I think a couple DOM-Us doing other things on that system. So yeah.
What are the hardware requirements for, how small can you get if you're going to do this on an embedded system? For instance, I'm on a 450 megahertz single core ARM system with 64 meg of RAM and 70 of disk. Could I get away with RTOS?
Probably not. And the reason is this. So Zen on ARM, I believe requires, but I'm sure as soon as I say this, someone's going to object and I'll learn that I'm wrong. But I believe it requires the hypervisor extensions for ARM, which means that you'd need a fairly modern A15 or A9, I believe. So I'm guessing that you are not in that class of chip. Once you get to that class of chip, then I don't think it really, at that point, matters how much memory or speed you have to some extent. I mean, clearly you have to make the real-time requirements of your system. But it's more you have to get to a certain class, and ARM believes those are mostly for servers and workstations and not for embedded in tiny things. So,
last question. How involved is the build process for an application on a unikernel? So if I've got a legacy application and one version has a different library and the other one gets rid of a few libraries, we're talking about a different unikernel from version to version of that application. So how involved is that build process then?
So it depends on the unikernel and it depends on the platform. I mean, I'm not sure I can answer that for all unikernels, especially if it's something in C, for example. Actually, I would ask the person sitting right next to you about how hard that is. I would say for FreeRTOS, for example, it would be just like compiling it for a different chip, in the sense that FreeRTOS basically treats the underlying platform as a library, which you link in the layer and it all works out. We just have a different one, which is the Zen one, and so you just have to switch your compiler flags, and hopefully it should just work. Especially in embedded systems, because you've already had to go through the care of making sure that you have exactly the right pieces of the right libraries you need, which is usually the hang-up on bigger systems. So hopefully with like a real-time system running on FreeRTOS, it shouldn't be that bad. I mean, it should just be a couple changes to your makefile and everything just works magically. But I probably shouldn't have said that on a live recorded medium. So. I get all the questions.
This is the most important one on everyone's mind. Was there any harm to the bunnies making this presentation?
There was not only was there no harm to the bunnies in the presentations, but I would like to also like to mention that all trademarks, service marks, trade names, trade dress, product names, and logos appearing in these slides are the property of their respective owners, including in some instances my employer Galois Inc. And so all rights on these slides are reserved. And you can thank Jody LaRue, who is our corporate lawyer, for that little blurb. All right. I'm about to run away, so cool.